Let's record this. Okay. All right. So in our last class, we have started learning numerical techniques of solving initial value problems. We are going to learn how to solve initial value problems in today's class also, but this time using RK methods. Yesterday, we learned about Euler method and the modified version of Euler method. Now, I'm going to recap some of the ideas from our last class that in modified Euler method, say for example, our original curve looks like this within the interval a to b, the interval in which we are trying to solve our initial value problem numerically. And let the initial value problem look like this. Let us consider the equation dy by dx equal to f of xy with the initial condition y at x naught is 1, just like yesterday. So the main idea was we draw a tangent line at a point, at the starting point. Then what we do is instead of finding the value of y at okay, I think I need to do a little change here, make a little change here. Say this is x naught, and say this is the immediate next point x1. Overall, say this is b, so probably somewhere there is x2 and so on. So let our curve be something like this. And we want to find an approximate value of y at the point x1, but instead of, we will probably not be able to manage this value, but rather we approximate by this value. So there is a margin of error, which is E1. This was the main idea. And the equation for Euler's method was yi plus 1 is equals to yi plus h times f of xi comma y. And we can start the process at starting from x naught because we know the value of exact value of y at x naught. Now, we are going to propose a little different, a little further modification in the equation, in this equation. Let's see how we do that. Okay, the first thing is to be noticed that when we modified Euler's method, what we did was we thought of drawing another tangent at x1, and what we did was we moved along the bisector of the two tangents. So we move along this line. So technically, if we moved along the tangent at x1, we would move along this line. This would produce a bigger margin of error, of course, but instead we moved along this resultant final line so that the error is reduced. This was the idea of modified Euler method. Now, today, we are going to propose a little different method. What we are going to do is choose the midpoint between x0 and x1. So this point is exactly x0 plus x1 by 2. There is another way of writing this. I hope you all remember that we assume the subinterval lengths to be equal to h. So we can just write this point to be x0 plus half of h. x1 is x0 plus h. This midpoint is x0 plus half of it. So what we are going to do is draw a tangent at this midpoint. And we will move along this pink tangent line, which has almost same slope as the arrowed blue line, right? So in a way, this gives a better result than typical Euler method. So, so for this new modification, the equation should look like this if you think logically. That is yi plus will h times f of f. The function f is the value of the slope at any random point xy, right? Which is on the curve, of course. So this time we are using the midpoint. So it should be xi plus this time is xi plus h by 2. The x coordinate of the midpoint is xi plus h by 2. Now, what should be the y coordinate of the midpoint? Now, this is a concerning question, right? Because we don't know what the value of y is at this particular value of x. Actually, other than x naught, there is no point in the entire x axis where we know the exact value of y. This is the reason we are trying to solve the differential equation numerically in the first place. So we do not have the value of y at this xi plus h by 2 point. So what we can do is, again, just like yesterday, when we use modified Euler method, we required yi plus 1. You can remember that. But the idea was we were in a situation where we needed the value of yi plus 1 to evaluate the value of yi plus 1. That is why we used the regular Euler equation, regular Euler method equation, right? We are going to do the same here as well. So what we are going to do is write h by 2 into f of xi comma yi. So we are approximating the value of the y coordinate at this point, and we are using, oh, I forgot to write yi plus 1. So here I should have written yi plus. Let me rewrite this segment. Euler equation, regular Euler equation is the same equation written in brown color here. We are going to use the same equation. So simply yi plus, usually, typically it would be h times f of xi comma yi. But here we are not moving up to the next point, but halfway through the path leading to the next point, right? So that is why we are adding a half here. So this is an approximate value of y at x naught plus xi plus h by 2. So what we did is to sum everything up. What we did is we used the slope of this pink line instead of the slope at exactly xi point. We use the slope of the tangent drawn at the midpoint between xi and xi plus 1. So the
Sir,
main,
how
yeah,
are we getting the next point using this method? I'm not clear about that.
uh, you are concerned, you are confused about this part, right?
No, I'm confused about how we develop this line. Like, I understood what we discussed yesterday, but
Hmm.
why are we considering this pink line in between?
Were you absent from the beginning of the class? Were you late?
No, I was here, but
Oh,
I'm not being
okay,
able to
okay,
understand.
okay, okay. Let me use different wording so that I can make it uh, more understandable this time. So original, you can understand that. Okay, let me use blue color again. Follow these blue line that has 3 arrows. This blue line is the tangent that we used in modified Euler method, right? You are okay so far?
Yes, sir.
Now try to visualize that just the way this blue line is giving you lesser error. Using similar logic, you should be able to visualize that this pink tangent line, which is drawn at the midpoint, should give you a better result. Let me draw two more tangents. All right. So consider this tangent which I just drew, the brown line, which is for this particular example of drawing, which is steeper than the pink tangent line, and follow the tangent line drawn at the next point, which is flatter, right? So at the midpoint, the tangent line should have a slope which is somewhat kind of average of the two slopes of the two tangent lines. Can you feel that? We are dealing with
Why
all
should the
approximations.
slope?
Okay,
Sir,
okay.
why should
Can
the
you
slope be an average of the two?
say this is a point? This is a point. First of all, consider that say this is the y-axis. So this is x1 and this is x2. We have a very small value of h, right? H is not as big as it uh, appears in this drawing, first of all. Second of all, the function or the curve is continuous between these 2 points. So in most cases, or almost in all cases, the rate at which the slope changes is very small. There isn't going to be a rapid change mainly because we generally choose very small value of h. Are you okay so far?
Yes, sir.
So it's expected that the slope of the tangent will change gradually. So it will gradually, at this point x naught, the slope, let me use another color. So at this point x naught, the slope has a high value. At this point x1, the slope has a low value, and the slope changes uh, almost linearly. The rate of change is almost linear as we move from x1 to x2 because h is very small, right? So the value of the slope, say for example, here is m1, and the value here is m2. So my claim is this will work as kind of an average of m1 and m2. It will not exactly be m1 plus m2 by 2, but it will be very close to m1 plus m2 by 2 because the slope is changing almost in a linear rate as h is very small. Can you see this now?
Yes, sir.
All right. So we are going to, we just use this idea in our last drawing. So the improvement of the advantage of modified Euler, you can recall that advantage of modified Euler method, right? Using the mid bisector of the two tangent lines was giving us some advantage. We are going to have similar advantage if we just use the slope at the midpoint. And even in this drawing, you can see that the slope at the midpoint, the pink line, is almost parallel to the blue line, which has 3 arrows. You can do the same here as well. So this is the tangent with slope m2, and this is the tangent with slope m1. Their bisector will be something like this. So if you draw, we already drew a tangent line here, and the slope of this line and this line are almost identical. And they will be even further more identical. It will be more difficult for us to distinguish between them if we choose h even smaller. Are you convinced now?
Yes, sir.
All right, okay.
So is our second claim that the translated bisector is parallel to the tangent?
Uh, we are not claiming that they are parallel. We are claiming that they are almost parallel, and in most drawings they will be. And I'm giving emphasis on this particular statement because you were convinced yesterday or in our last class that the bisector gives us advantage. if the slope of the tangent line at midpoint is almost identical to the slope of the bisector, then we will have similar advantage using the slope at the midpoint as well. This is the main idea. So if you were convinced that the bisector gives us advantage in our last class, you should be convinced now that the tangent line at the midpoint gives us similar advantage in today's class. All
Yes,
right.
sir.
Okay. So yi plus the p, this equation is going to give us almost equally good result, as good as Euler modified Euler method did. Should theoretically it should, and this this method is called midpoint method, and it has another name. I find it really difficult to pronounce the name of the two mathematicians. Uh, it's in short, it's called RK. So it's called RK method of order 2. In fact, the shortest name it has is RK2, the RK2 method. When I say RK2 method, you should understand that I'm meaning RK method of order 2. Now, you must be having some questions. Those who are not familiar with this idea should have some questions here at this point, because if we have RK method of order 2, there must exist RK, at least another order RK method, right? There should exist at least one more RK method that has a different order than 2. And there is actually another popular method, which is called RK4, or RK method of order 4, which uses a very similar argument, which uses the fact that the line, the direction along the tangent drawn at the midpoint is very useful and gives less error margin. This fact is going to be used in RK4 method as well. But RK4 method also uses idea of average. You see, basically, the equation I just developed, the equation for RK2 and the equation I'm going to write for RK4, both of these can be derived using Taylor series mathematically, analytically. Derivation for RK2 is a little compact, but derivation of RK4 is a long one, very rigorous. But since this is not a numerical analysis class, but rather a programming class where we are going to write a program that implements these methods, that is why I'm not going deep into the derivations, the analytical derivations, but rather I'm just trying to visualize them geometrically and trying to make you visualize them geometrically. So basically, you must know the idea of average and weighted average, right? For example, your CGPAs are actually weighted average. If all the courses had equal weight, then you would not need any weighted average. You just add them all and divide by the number of courses. But unfortunately, we do not have equal weight for all the. Mubashir asked a question. I request you to ask this same question at the end of this class so that the momentum is not lost. All right. Okay. So I was talking about what? Okay, average. So if all the courses had equal weight, then we would just add all the GPAs and just divide by the number of courses. But unfortunately, this is not the case. When weights are different for different courses, you have to apply the formula for weighted average. For example, if you got 3 in a course with 3 credit weight and 4 in a course of 4 credit weight, then your CGPA, if you had just 2 courses, imagine a very ideal world where you just have to study 2 courses to graduate. So the CGPA would be just divide by 3 plus 4, right? Whatever the value be. Now, now you can understand that if I just write 3 plus 4 by 2 and say that you got a CGP of 3.5, it would be an injustice. It would be unfair to you because you got higher GPA in a course which has higher volume of syllabus, right? Higher volume of content to cover. So you should be given some extra credit for that. For example, if a friend of you got 4 in the 3 credit course, but 3 in the 4 credit course, and if I say that you two should get the same CGPA, that would be unfair, right? That is why we introduced the weight. Now, here is the thing. Since we have observed that the tangent line, the value of the slope of the tangent line at the midpoint is more useful than the slope of the tangent lines at the exact points x1 and x2. Let's use all three of them. Let's use the slope of the tangent at x1, the tangent at x2, and the tangent at the midpoint. Let's use all three of them. How so? Like this. Basically, give me a moment, please. Here is how it's done. We assume 4 variables, k1, k2. You can find these equations in the book of Burden, a book that gives you a lot of burden. Okay, so k1 is h times f of xi comma yi. So what is k1? Technically, k1 is in the Euler method equation. You can see that we actually use k1 here. So k1 is in a sense the increment in y when you move along, move from xi to xi plus 1 to the next point. So this is the value of the increment of y in a sense. K2 is h times f of xi. Now we go to the next midpoint. Okay, so this is xi. This is xi plus h by 2, the midpoint, and this is xi plus h, which is xi plus 1. Let's, we just need these 3 grid points and nothing else. So let's just draw this only. Okay. So f of xi plus h by 2. So we increased x by half h. So we are actually trying to write the slope at the midpoint. To write the midpoint, we write yi plus k1 by 2. And you can see that this is the exact equation for RK2 method. We approximated the value of y using almost the equation of Euler method, right? So far, nothing is unfamiliar. But K2 is h times f of xi plus h by 2. So this is again the approximation of the slope at the midpoint. And this time we write yi plus k2 by 2. So k2 is, in a way, you try to observe that h times slope. H times slope is, in a way, the increment of y. So k2 is kind of an approximation for increment of y. But increment of, since we are using h here, but not h by 2, it means it actually means increment up to the next point, not up to the midpoint, but up to the next point, because we used h here. So technically, this was the increment of y. We use the same value here, but half of it. That means we increased yi by half of the approximation of increment of y when you move to the next point. So technically, this should also work, but this would actually give a better approximation of the value of y at the midpoint. And again, we are multiplying it by h, not h by 2. So this is again an approximation for increase in y when you move up to the next point, but not midpoint, next point. And k3 is just h times f of xi plus h and yi plus k2. Now you can see that k2 is actually increment in y when you move to the next point. So technically, yeah, that's all basically. Nothing left to say. So these are
K2 and 3. We have two
yes.
K2s there. So which one are you referring to?
Okay. I think or I mixed up something. Let me edit this. It should be K3 and it should be K4. It should be K3. Okay. So this is K3 and this is K4. Thank you. K3. So K3 is another better approximation for increment in y when we move from xi to xi plus 1. So if we move from here to here, increase in y is actually K3. It's also should be very close to K2 also. Both of them are approximation for change in y when we move from yi to yi plus 1. And we use that value of y here to find K4. Now, you can understand that K2 and K3 were approximated. In a way, they involve, if you divide K3 and K2 by h, you would get the value of the slope. So technically, since h is constant throughout our process, h can be considered as a scaling factor only and nothing more. In that sense, K2 and K3 are proportional to the value of the slope. But slope at which point? Answer is at the midpoint. So technically, these two guys are values of the slopes multiplied by h evaluated at the midpoint. But K1 is at xi, K4 is at xi plus 1. These two guys are at xi plus h by 2. So technically, we have four values of increment of y. We have to average them. But when we average them, what we do is we do not just calculate regular average, but weighted average. We increase the weights at the midpoint. How so? We multiply by 2 here and here. And since we have weight 1 plus 2 plus 2 plus 1, we divide by 6. So this is the average of the increments of y or del y. So overall yi plus 1 should be yi plus this average. This is the main idea of the RK method of order 4. You can understand why we are mentioning order 4, because we used up to 4 Ks. So this is the main equation of RK6 method along with these 4, of course. We can replace these 4 values from these 4 equations and make a single equation instead of 5 different equations, but that would produce a very, very complicated looking equation. That is why we are going to stick with the 5 equation set. Is there any confusion anywhere in the process or algorithm or development of the equations?
Sir, how do we know that the error is being decreased and not increased from the repeated approximations that we are taking?
Okay, the logic is simple. The slopes at x1 and x2 were going to produce greater margin of error for sure, right? But when we were using the slope at the midpoint, it was producing lesser error. We could see that visually. And technically, you could just say that why don't we just discard x1 and x2? Basically, we could do that, but modified Euler method showed us that taking average of x1 and x2 would produce something of a lesser of a margin of error, right? So that is why we kept the slopes of at the points x1 and x2 as well. I mean xi and xi plus 1. So we kept them. Technically, they were averaged anyway. K1 and K4 were being added and finally divided by 6. So they were we were taking the average anyway of the two guys. We just increased the weight at the midpoint because midpoint was producing lesser margin of error. And basically, Ilham, to answer your question, if you see the one could argue that we could just write 3 instead of 2 here and here. In that case, we had to divide 1 plus 3 plus divide by 1 plus 3 plus 3 plus 1, which is 8, right? That could produce probably lesser error. But technically, all these arguments are just geometric interpretations of the already derived formula derived using Taylor series. So Taylor series would contradict if we just used 3 and 3 here and divided by 8. So what I showed you is not the concrete proof, but a motivation or geometric interpretation of the already analytically proved results. Am I clear?
Yes, sir.
All right. Okay, now let's move on to the coding part. We are going to write the code for this new method. RK2 is easy. Let's code.
Sir, in the last final stage RK4, you've labeled it RK6.
Okay, that was a mistake. It should be RK4. Give me a moment, please. I just disconnected my graphics tab. Yes, it was a slip of pen, of course. It should be RK6. And okay, my goodness, I wrote 6 again. And it should be understandable that there exists a method called RK6 as well. We do have an RK6 method, but we generally don't use that. We will see later why I did not show RK6. There is a logic behind it. Okay, let's move on to coding. Let me start run code blocks first. In Barden's book, at what page? The theories are here, but I'm interested in the problem. Okay, here you can see that this is page number 289. All right, page number 289, and Barden's book solved the same problem we solved yesterday. We solved the same problem in our last class using Euler and modified Euler method. They solved the same problem again, but this time using RK4 method. We are going to do that and see how if there is any improvement in the results. Okay. File. First of all, let me open the. Okay, do you remember that modified Euler method finally produced much lesser error than Euler method did? You can remember, I think. So just run the code again for a single time to see how the error margins look like. The errors were in 10 to the power minus 2s and minus 3s, right? So this is to brush up our memory about the error margin. And also, since we are going to solve the same problem, a good portion of the code is going to be repeated. That is why, first of all, let me copy the entire code. Control C. Let me open a new file. Control V, and let me save it with the name rk4.fp. Okay, so let me change the name of the program also, rk4. All right. Okay, if the meeting ends abruptly, we are left with 1.5 minutes approximately. So if the meeting ends abruptly after 1.5 minutes, please rejoin using the same link. And I have applied for a pro version using BD Rail. Okay, so maybe this problem will not continue any further from our next online class if there is any. Okay, what changes should there be? That we need a T array and an Y array. We need A and B. We know Y naught is 0.5 because same problem. We need the right hand side F, the actual solution. We need H, we need error. All of them we need, but we also need 4 new real variable K1, K2, K3, and K4. Okay, we need to create the array Ti just like last class, but we are not going to use this equation, of course. So first of all, let's write the equations for K1 to K4. I think the two functions will remain unchanged, and the writing part, printing.
For be arrays, we will have different values at different points.
Okay, you asked if there is going to be if we should write arrays for K1 to K4, right? I don't think so. We'll see why. Technically, in each loop, we need to calculate x1, x2, x3, x4 at every I, right? But we are not going to reuse that k1, k2, k3, k4 later anymore. So we don't need the array. You will see. Let's write what I was saying, that I need these two functions. So let them stay. And I also need this writing statement. Let it stay as well. So I think everything else should be as it is. So K1 is, from our theoretical discussion, K1 is H times F of, we have Ti, there it was Xi, but here it's Ti, comma, Yi. So this is K1. Let's copy this line and paste again. Write K2 here. H times F of Ti should be increased by H by 2. Yi should be increased by K1 by 2. Now copy this last line and paste and make necessary changes to make it convert into K3. So Ti it's still midpoint, so Ti plus H by 2, but here I need to use K2. And finally, we should write the equation for K4. So K4, H times, now we are at the point Xi plus 1. So no point writing the by 2's anywhere. Here we should use K3. Okay, now Yi plus 1 should be Yi plus, simply basically remove everything here. The weighted average part, right? So bracket K1 plus 2 times K2 plus 2 times K3 plus K4 divided by 6. So this should be enough. We have the error here as well. I think it will do. Now, Ilham, did you get your answer that K1, K2, these need not be arrays?
Yes, sir.
All right, okay. Now let's run the code. I hope there are no errors. Okay. The rightmost column is the error column, and you can see the error margins are in the 10 to the power minus 6s and 5s. But if I run the modified Euler code again, which was modified Euler improved the results from Euler method by a big margin. So modified Euler was already a very good method, but RK4 even improved it much more, right? The improvement from modified Euler to RK4 was even bigger. So now the question, basically this is a very surprisingly good result. You should understand that we have only used H equals to 0.1. And using H equals to 0.1, we found that the error margins are almost proportional to H to the power 5 or 6, right? So just there is just one point where the error has 10 to the power minus 4. So technically the error margin is in order of h to the power 4 here. So this is a very, very good method. And there is a proof also to the claim that RK4 method produces errors in orders of h to the power 4. The proofs are in every numerical analysis books. So technically, we have a great method here. We can improve it even further, way further. If I just somehow write another method or derive another method for RK6, and RK6 exists in different books, but technically, you can see that the loop runs from 1 to n times, and each times we are evaluating the function quite a lot of times, to be honest. So if we increase number of equations here up to k6, the computational complexity increases, which is a disadvantage. So you win some, you lose some. So we decide that RK4 is good enough for us. If we try to make further improvements by introducing RK6, computational complexity increases. Also, that is why we stop here. Okay. Is there any question? Is there any question? Okay. All right. So this is RK4, and technically, this is all I wanted to include in today's lecture. I am going to post an offline assignment 3, and the assignment would be the same problem I provided in assignment 2, the differential equation of simple harmonic oscillation. But this time you need to solve it using RK4. Now you can understand that in our last class, we had to convert the second order differential equation into a system of first order differential equations. We need to do the same for this case here as well, because RK4 is also a method for first order differential equations, not second order. So you have to convert the equation similarly to a system of first order equations. So there will be 2 differential equations, and you would need to solve them simultaneously. So you would need 2 sets of K1, K2, K3, K4 for the 2 variables. You can choose different names for the set of variables for the other differential equation, maybe L1, L2, L3, L4, or something else. All right, and that would be all. If there is no questions or confusions, I want to end the lecture today. Okay, see you all in the next class. Oh, one more thing. Yes, last class I declared that the syllabus of mid-exam is up to the class we are going to take on next Thursday. But I think there will be very little time for you to prepare the topics on that class. That is why the syllabus would be the topics that I covered up to today's lecture, up to RK4 method. Is the syllabus clear?
Yes, sir.
Okay. Okay. See you on next class. I'm going to end the meeting now. Oh, I just remembered someone asked a question, maybe Mubashir, at the beginning of our class. What was the question? I asked him to repeat the question at the end of the class.
I think he was like, what if we have the H in the Euler's method?
Okay, okay.
And let's give the same thing.
Okay. Basically, I think it would take 4 or 5 minutes to answer. Okay, to answer his question, if I'm not wrong, his question was, what would happen if we just half the value of H, but use the same method? Okay, decreasing the value of H will give us better result for any method, because in most methods, if you go through the Barden's book or any other numerical analysis book, you will see that the writer generally develops the order of the error in powers of H. If I am not wrong, modified Euler or Euler method, probably modified Euler method has error margin of order of h square, if I'm not wrong. Please verify this. So I'm writing a question mark here. So this is modified Euler method, and RK4 method has, I think this one is, I'm certain of, RK4 method has order of h to the power 4. So if you half h in RK4 method, the error margin would decrease, basically would be 2 to the power 4-fold improvement there, right? The errors would typically be 1 over 2 to the power 4 times the error if we just half the value of h, and this would be applicable for every method. In every method, there is an error margin that has an order of some power of h. All right. So yes, one thing we could do is just use lesser h in modified Euler method. It would give similar improvements like we got in RK4, but there is one problem. If you decrease h, it would increase n. That is, if you half the value of h, the value of n would be double. This would mean double computational complexity. So it would be better if you can find a method that does not require the value of h to be too low to produce good results. And RK4 is of that kind. I hope that clears Mubashir's question. Okay, he said yes. Okay. Okay, so is there any more questions? All right, then let us end the meeting for all for today.